Okay, so welcome to 15859, I guess double G section, and this is the first lecture for proofs versus algorithms, the sum of squares method. So let's start with some basic information about how this course will run and what we might have to do. But like the zeroth level announcement is that we are all kind of winging it in terms of online teaching here. And so we may have various hiccups. uh, we've tried to somehow anticipate a few and basically modify our strategy to adjust to them, but there might be a few more that pop up, and in that case we might have to make modification on how we do the course. Like we might have to, for example, shift from Zoom to YouTube streaming or whatever. I expect that this would be fine more or less, but just to let you know that there might be some changes that we could have. The other thing is that I I recommend, if you can, then it would be great if you could turn your videos on. It's not necessary, and it's fine. For example, if you cannot, but if you can, that would be great. Great. Okay. So I hope you're all able to access Scribble, where we are going to write the notes. So this is going to be visible on the screen as you see, but also you can browse the notes, and you can like scroll independently if you access it via browser. So this is going to be once a week. We'll meet once a week for this class. It's going to be a 3-hour lecture, as today. Um, we'll basically have one break in between. So around 5:30, we'll take a break of, let's say, 10 to 15 minutes. Well, yeah, and that's the only break that you'll that we'll have in the lecture. So I think all of you, at least people who've taken it for credit, are already on Diderot, which is what we'll use for discussions, questions, announcements, etc. So far, I've been emailing most of the important announcements because all of you may not have been on Diderot already. But as basically the course stabilizes, I'll shift completely to Diderot and like not have any other email announcements. Regarding evaluations, so as the course website says, we're going to have 4 to 6 homeworks. Homework 0 is already, you must have received it. And actually, it's quite a few of the problems in homework 0 we are going to rely on today to prove things. So that's going to be super useful today. So in general, we'll have 4 to 6 homeworks, and that will be part of your grade. The other component in your grade would be a set of expository notes that everybody would write individually. And I'll explain to you, how this will work as the course goes on. So expect more information about it in the coming weeks. Good. Finally, office hours. So I'll have my office hours on from 10 to 11 a.m. on Wednesdays. And Peter, who is our TA, Peter Manohar, you can see him, I guess, on the call here, is going to have his office hours 2 to 3 p.m. on Mondays. Okay, great. That's all the administrivia. Let's begin. So let's maybe start by just understanding what is this class all about. Like what are we going to learn? So the title is title says it's about the sum of squares method. And what this is just a method to reason about two basic problems about polynomial inequalities. Okay, so let's write down these problems. So the first problem that we are interested in is checking feasibility of polynomial inequality system. So basically you have a bunch of polynomial inequalities, and these are all over the real numbers. Okay, so you can maybe look at it like this. So you have P1 x bigger than or equal to 0, so on up to Pm x bigger than or equal to 0. And here x is an n-variate indeterminate. So it's just a vector of a vector that is supposed to take real number values. Just a second. Okay, good. So given such polynomial inequality, so the coefficients are going to be real numbers. We're going to think about the computational aspects of it in a second, but for now it's maybe simpler to think of them as just real numbers. So you're given a bunch of m real polynomials. They are n variate polynomials, and the question you are interested in is is there a x such that all these inequalities are satisfied? Okay, so this is the feasibility problem. And actually, we'll also study a related question, which is, checking positivity. So, it's basically the problem where in addition to this m polynomials, you're also given a, m plus 1th polynomial, if you will. And your goal is to decide is qx bigger than or equal to 0 for all x satisfying the system 1. Okay, so those are two fundamental problems that we're interested in. And so it might a priori appear like weird that we're going to basically run a whole class about these problems. So let me try to justify why it's actually sensible to teach a whole class and actually more about just these two problems. Okay, and so the reason, as you might expect, is that the feasibility checking problem, for example, is very expressive. Like it captures a number of interesting problems that we all care about. So let me give examples, because that's how I can justify expressivity to you. So I assume that you all heard about the max cut problem. So in the max cut problem, your input is a graph GVE. V is the vertex set, E is the edge set. Let's say we have n vertices. Okay, and the goal in the max cut problem is to find a subset of vertices. Actually, so find a subset of vertices such that the number of edges that go across S is maximized. So let me actually let's maybe write it in notation just like this. So by ESS bar, I just simply mean the number of edges that go which have one endpoint in S and one endpoint in the complement of S inside V. Okay. So let me convince you that this problem is an example of the feasibility problem that we just defined. Okay. So let's say that so for some number, for some integer number, let's say beta, consider the following system. So here is a polynomial that I'm going to write. Okay, so I claim, so first of all, before even interpreting what I have actually written here, you agree that this is a system of n+1 polynomial equations. Okay. And as I said, we are always going to think of these polynomial equations, over the real numbers. So we have a system of n+1 polynomial equations. And I'm actually now going to convince you that this system feasibility checking problem is actually equivalent to asking if there is a cut in the graph G that cuts beta times E number of edges. Okay, so beta fraction of the edges. Okay, so why is that? So let's look at this system of let's look at the constraints xi square equals 1 to begin with. Okay, the only solutions to xi square equals 1 for 1 less I less than n are basically vectors x which take the values in the Boolean hypercube plus minus 1 to the n. Agree? So this system basically means that x can take values only in plus minus 1 to the n. Very good. Now it's natural to associate any vector in plus minus 1 to the n to a subset of vertices by, for example, just thinking of the set of all vertices for which x has the following coordinate 1. Okay. Now let me convince you that if you take this set indicated by any vector x like this, then the value, the number of edges in the cut described by it actually equals this degree 2 polynomial that I've written down here. Okay. Why is that? So, basically this polynomial has a quadratic term for every edge of the graph G, right? Now let's understand, if I have a vector x, what happens to a certain term corresponding to an edge. So if you look at an edge I comma j, then xi minus xj can only take two values when x is over plus minus 1s. It either takes the value 2 or it takes the value 0. If I and j happen to be on the same side of the cut, then xi and xj are equal, in which case the value is 0. In the other situation, when the edge is actually in the cut, the value that xi minus xj takes is 2. The square of it takes the value 4. And this 1/4 outside basically normalizes it to 1. And so because I'm summing up over all edges, you can see that basically I'm counting the number of edges in the cut described by, x, where we are thinking of x as describing a set of vertices. Okay. By the way, if you have any questions, feel free to stop me and ask away. Good. So good. So you see an example right here. So MaxCut is an example of a degree 2 n plus 1 polynomial feasibility checking system. One thing you might be actually wondering about, by the way, is that I stated MaxCut as a maximization problem, while here I described like a feasibility checking problem. But it may not be very hard to see that I can just run it for all possible values of beta. There are only polynomially many values to check. So I can check it, check feasibility by varying beta. Right, I can basically, if there are m total edges, I can run this feasibility program with cut size m and m minus 1 and m minus 2 and so on. And so, that gives me a way to solve m different polynomial feasibility problems. And, in order to solve the max cut problem. Okay. So you might all be, already troubled about the algorithmic aspects of this, like how long is it going to take and all. But we'll come to those situations, those issues in a bit. Okay. Here, my only goal is to convince you that this polynomial feasibility is an extremely expressive problem. Okay, so that's the max cut problem. By the way, this particular expressivity thingy already proves that polynomial feasibility checking is NP hard, just because we simply encoded max cut right away. So one thing we've already learned about the problem we are interested in is that it's NP hard. Good. So so that's an example, but there are many examples that fit the same bill, which I'm not actually going to do them explicitly here. But other examples include, for example, the max click problem, any max CSP. So for example, max 3SAT problem. Actually, you don't need to be a CSP, so you can encode problems like knapsack if you heard about it, etc. Okay, so basically, many of your favorite combinatorial optimization problems can be encoded very simply as low degree polynomial feasibility problems. Like I didn't even state a degree bound, but for example, you saw that max cut in fact has polynomials of degree at most 2 appearing in it. And max 3SAT, actually, if you do the same thing, would happen to have polynomials of degree 3 appearing in it. So in general, the degree of the polynomial that appears is just a constant. And even degree 2, as you saw, is expressive enough to capture NP-hard problems. Good. All right. So what's our goal? We have kind of already, convinced ourselves that polynomial feasibility is NP hard. And so, we have to, in some sense, be modest in our expectations. What are we trying to do? So we're trying to, in some sense, analyze a relaxation for the feasibility problem. Okay. This relaxation is, in fact, the sum of squares method. And try to find interesting situations where actually it's going to give us good guarantees, whether by solving the problems approximately or things like that. So try to find interesting situations where we can get, efficient algorithms. Okay.
Hey, Pravesh, Lenore
Yeah.
has a question in the chat.
Uh, okay. Can you read it out to me? I don't know exactly how to access it, I guess.
She just asked, what do you mean by NP hard when your constants are real numbers?
Right, good. So again, like I haven't specified the input model here, and I haven't even told you, what kind of computational model we are interested in here. But so in some sense, this is part of the part of the motivation part of the lecture. But just to answer this question, for the problems I just described, we are supposed to think of all the coefficients of the polynomials as rational numbers with polynomial bit complexity. So every coefficient of the polynomial is going to be a rational number where the numerator and denominator are integers that can be specified by polynomial in, let's say, a small n, the number of variables, number of bits. Okay. And so just like actually for the example that you just saw, max cut problem, the encoding in fact had coefficient which were just numbers like 1/4. And so in some sense the bit complexity is not even polynomial in some sense. Good. So, and we are going to discuss the most general case soon. And so we'll then, and at that time we'll specify the model more clearly. But right now, I guess my only goal was to specify that because it captures the max cut problem, in any reasonable interpretation, we'll end up with an NP hard question. Good. All right. So, so I have not told you what the sum of squares method is, but that's what the whole, course is about. And I'm going to describe it to you very soon, but I kind of want to give you a little bit of historical interlude here before diving into it. So this sum of squares method, which is like a way to relax this feasibility checking problem, was studied from multiple different perspectives in several different fields, and actually for a while completely independently of each other. So for example, in computational complexity, which in some sense, I guess, is we can think of it as home area for the perspective of this class. In computational complexity, use of semi-definite programming is a focal point of research. And like I don't know if you've heard about semi-definite programming. We're going to define it a little bit later on in this class. But if you haven't, you should think of for now you should just think of it as a generalization of linear programming. And so semi-definite programming is like a super useful method of algorithm design in computational complexity. And in a sense, it was actually used by Lowash maybe in as early as 79. But the algorithmic power of this method, in some sense, was harnessed only after this famous result of Gomans and Williamson, who designed like an algorithm for max cut in 1995 using semi-definite programming. And since then, there is basically a whole lot of activity in this area of using, SDPs in algorithm design. And this connects to, things like Coates' unique games conjecture. How do you optimally solve all constraint satisfaction problems? And, questions like that. But nobody actually thought of it as a sum of squares method or anything. They were just solving semi-definite programming. You're thinking of them as a generalization of linear programming. From our perspective, these semi-definite programs that people studied actually are just going to be a very special case of the sum of squares relaxation of polynomial feasibility. So we'll learn that these are just special cases of the sum of squares method. And so in a sense, TCS has been studying at least some aspects of the sum of squares method since at least early 90s. Actually, there is a different area which was also studying the sum of squares method, but from a completely non-algorithmic perspective. So there is an area of computational complexity called as proof complexity, which studies the question of how complicated do proofs need to be for, let's say, certifying certain NP statements. Again, in the first part of this talk, if something doesn't make sense or if I'm using some terminology, feel free to ignore it because, we'll get to concrete things in a bit, like in 10 minutes or so. This is like a motivation part of the class. Let's see, is there a question? Okay, I guess we've already discussed that. Good. So in proof complexity, as I said, we are interested in finding out how complicated are proofs for proving certain NP statements. And in that domain, people invented what is called as the positive Stellensards proof system, which turns out to be basically the sum of squares method, in its non-algorithmic incarnation. And so they were proving, results about the sum of squares method without actually calling it sum of squares. And so, one of the pioneering works in this area is due to Grigoriev and Vorobyev from 1998. But these are, basically more areas which are like essentially, theoretical computer science. But, TCS is not the only field that studied this method. In fact, the formalization of this method came from optimization and control theory. So in what is like basically a classical work now, Pablo Perillo described a sequence of SDP relaxations. And he was interested in, formulating such relaxations to compute what are called as Lyapunov functions in control theory. Again, not our interest, but he defined his SDP relaxations as, methods to solve certain optimization problems that arise in control theory. And actually, about at the same time, Jean Lasserre defined a sequence of SDP relaxations to solve what is called as a generalized moment problem. And so, a priori, it doesn't appear related to us because it's not about, checking polynomial feasibility like Perillo was doing. But it turns out, and in fact, towards the end of the class, we'll see some aspect of a proof of this, that this turns out to be, in a very formal sense, the dual to, the positive checking problem, positivity checking problem or feasibility checking problem. And so, in disguise, Lasserre was just basically studying the dual to the SDP relaxations that arise in the sum of squares method. And actually, it turns out that these two were not exactly the first people who studied sum of squares either. There were some special cases of sum of squares optimization that were studied in maybe early 90s, actually late 80s, by Nesterov and Naum Shor. This is not Peter Shor if you're thinking about him. Nesterov and Naum Shor were studying, certain relaxations for polynomial optimization problems, and they invented what can be thought of as, a special case of SOS SDP relaxation that we are going to study. Anyway, so that brief historical note was supposed to just impress upon you that for whatever reason people came up with this method in very different contexts and from very different perspectives for solving very different problems. So what we are going to focus on is what I like to call the modern view, which for me begins in 2010s. And so in 2010s, really, in TCS, people started thinking beyond the kind of SDPs that Gomans and Williamson were writing to solve problems which are related to unique games conjecture. And in particular, they realized that they can use this sequence of relaxations that Perillo and Lasserre were playing with. And that led to basically a theory of great interest to TCS. And so we are going to study, this modern view, which is somehow, tailored to solving combinatorial optimization problems. And actually, in particular, CSPs, for example, like unique games problem, if you heard about it. And since, about 2014 or something, this modern view has actually led to new methods for designing algorithms for average case problems. So these are problems, where the inputs are not worst case, but rather they come from some distribution that you have reason to care about in certain situations. And so, in particular, this method gave like state-of-the-art algorithms for various problems arising in machine learning, statistics, and so on. And so we're going to see, this, we're going to focus on this modern view. We are going to, in some sense, go back and rephrase what Gomans and Williamson were doing in this modern view in order to somehow put everything in one unified framework. And then, we're going to see this modern applications from various angles. So that's basically, what we are going to do. So just to, specify our plan a little bit, in a little bit more detail, our plan is to study worst case algorithm design using sum of squares method using this modern view. And so, in this section, we'll, see questions like max cut, how to color 3 colorable graphs, solving the so-called growth and deek problem. And, we'll see how to, solve or approximate every constraint satisfaction problem and prove a result called as Raghavendra's theorem. Then, we'll see some aspects of average case algorithm design, as I was just mentioning. And, we'll study problems like finding planted communities, or if you heard about the problem of stochastic block model, that's an example of this. We're going to look at that problem. We're going to look at problems that arise in machine learning / statistics, like clustering mixtures of Gaussians. And other related problems. We're going to see how to prove lower bounds on this method. Like, how do you prove that this method actually cannot yield good algorithms? So we're going to see like some principled methods to approach proving lower bounds for this method. And so this will involve a foray into some geometry. We'll study techniques like pseudo calibration, which gives lower bounds for certain average case problems. And finally, we'll focus some lectures on connections of this method to other algorithmic methods / frameworks. So for example, we'll study connections to extended formulations. These are, certain principled ways of defining, in a certain sense, what could be thought of as the most general linear program or most general semi-definite program for, your algorithmic problems. And so, we'll study relationships to this most general SDP to, the SDPs that fall out of the sum of squares method. We'll study the so-called statistical query model and the relationship to sum of squares. So SQ model was defined in the context of machine learning. It's like a restricted algorithmic framework that captures many algorithms, and people prove lower bounds on this family of algorithms. We'll study how they relate to SOS. And we'll study a method that has actually gotten a lot of attention in the last 4 years or so. It's called the low degree polynomial method. Again, useful, for understanding problems in statistics. And we'll see, how this method relates to, sum of squares. So we kind of have an ambitious plan and several different aspects to cover. And so as you can expect, we are going to fail at it. At least I am going to fail at it, because I'm only going to pick like a couple, 2 or 3 applications from each of these, different goals and, explain them to you. So the way we will broaden our reach into these topics is, by the second part of your evaluation, where, you're going to write expository lecture notes. So the plan now I can actually clarify a little bit better. We have like several topics here, and actually they are listed in more detail in your syllabus that appears in the course policy document. Whatever topics we don't plan to cover in the class, which should be clear, let's say mid-October. Out of those topics, I would ask the registered students to, pick one topic and assume as if I taught a lecture on it and wrote lecture notes on it, and then write those lecture notes that would have been written if I had given a lecture. And you will do this individually, and these will be peer graded, which means that other people in the class will read and fill up a review form, which I'll generate. And so this way, our hope is that, okay, we won't be able to learn these topics in as much detail because not everyone would be working on every one of the topics, but we'll still get a good glimpse of it, by both writing the lecture notes and, reading the lecture notes that other people wrote. And so this way, our reach would be much broader than, what it would be if I were alone, lecturing. So that's our plan. Okay. Good. So if there are any questions right now, like as I said, this is the motivation part of the lecture. So if there were terminology that were, unclear, or if there were claims that were shady, well, I would ask you to excuse me for it. And from now on, I will not make shady claims. At least if I make shady claims, you can ask and I'll have to, make them unshady. So, but in any case, if there are questions right now, we can pause for like a couple minutes and take them.
Oh, hi. I was wondering if sum of squares has had an impact on the algorithms used in practice at all?
This is a really good question. So as I guess we'll see later today, the algorithms that we will talk about would usually have a running time which would be kind of large, which means that in any generic situation, we won't be able to talk about problems where the input size is, let's say, more than 100 or whatever. So for example, we might be able to practically solve max cut with the sum of squares algorithm, maybe if we are pushing it with like 500 vertex graphs or something. But I think more than that, I think may not be possible right now, even though there are faster algorithms which don't have to use SGPs right now. So we are not going to talk about, hyper efficient algorithms that could be useful in practice. But the answer to your question is yes. It turns out that there are settings where the natural settings where there are problems where the number of variables are very few, and you care about exactly or optimally solving SDPs that arise for such problems, because the application is somehow let's say very important. And so one such application actually appears in designing control systems for fighter aircrafts. And there's actually an aircraft which I now forget the name of, but the control system of which actually runs some degree 12 sum of squares relaxation on 16 variables. And so, that in some sense, the most practical application that I can think of right off the top. The other algorithm that we can see, it turns out that, it's, I didn't mention it, but let me write it down here. So we are going to see, if time permits, we'll see maybe one lecture on how for certain problems, after you've designed and analyzed a sum of squares based algorithm, you can actually somehow extract a much simpler and potentially faster algorithm from it. And so this is like a very recent and nascent research direction. It builds what are called as spectral algorithms from sum of squares counterparts. And for some problems, you can actually get hyper efficient algorithms this way, like even linear or nearly linear time algorithms. But again, I think the point is that most of the stuff we are going to see in this class will not be very efficient in practice, because that is not our goal. Like, our goal is to illustrate methods how to design polynomial time algorithms and reason about them. There are applications, but perhaps not as many as you would like. And it's an ongoing research direction on how to make this methods more efficient and make them work in practice. Good. Okay, so let's begin doing some actual math. So in order to somehow motivate the central concepts and do things very concretely, we're going to look at a very special case of polynomial feasibility to begin with. Okay. So in the first, I think 3 lectures, including today, we're going to look at problems of the following form. The input will be a polynomial on the Boolean hypercube with rational coefficients, and the goal is to decide if f is bigger than or equal to 0 on all x in plus minus 1 to the n, the Boolean hypercube. Okay, or conversely, you could ask, or find an x such that fx is less than 0. Okay, so just maybe some comment about notation, and also like take a natural pause so that if there are questions, I can always answer them. So I'm going to call plus minus 1 to the n the Boolean hypercube. You might have seen 0, 1 to the n used for it. In basically all the situations that we're going to deal with, you can go between them interchangeably. This notation is somehow more helpful for me, so that's what I'm going to stick to. Okay. And yeah, so one example that we already saw of this problem was the max cut problem. So let me explain to you that max cut in fact is a problem of this sort. So it's not a completely boring exercise to look at this question. Okay, so suppose you want to decide. So you're given a graph G, GVE. then we already saw that there is a degree 2 polynomial that computes, the size of the cut described by, the input x, right? So let's call that polynomial fg of x. And we actually saw its form. It's basically this quadratic polynomial. So fg of x, as you vary x, computes, the size of the cut described by the set indicated by x. And so let's say you want to decide if max cut of G is at most some number C, okay? Then that's the same as testing whether C minus Fg of X is identically non-negative on all X in the hypercube, right? Because if the max cut is at most C, then for every X in the hypercube, this polynomial which computes the size of the cut must be at most C. So C minus Fx must be non-negative. And so testing if C minus Fx is non-negative is basically equivalent to deciding if the max cut in G is at most C, okay? And so you can see that, if you could solve this problem, then you can solve max cut. And, and in particular, problem 1 is NP hard, but we're going to look at, what we can do about it, when can we approximate it, and things like that, okay? So I already talked about, I guess, F being, I already said, the F will have rational coefficients, but we should think about the questions of representation. So in problem 1, the one thing you can ask is, how is the polynomial F presented to you? So throughout this course, and in particular today, we're going to assume that Fg is given to you by describing to you every coefficient separately. Okay, and we said that F has rational coefficients. So we're just going to, use we are going to just describe the two integers that describe every, rational coefficient for F. Okay, so in particular, this is a finite bit representation of the input, and our goal would be to understand, what can polynomial time algorithms in this representation do? In particular, what does polynomial time SOS method do here? Okay, good. We're also, going to look at a very related question, which I'm going to call the certifying version. Which you can think of as, in some sense, asking for more from a solution to problem number 1. So in this case, we are given a polynomial F, and we want to understand, so when Fg is positive, sorry, I should not, there is no G anymore. So we want to understand non-negativity of F, and in particular, if it is non-negative, we want to produce a certificate of non-negativity, okay? And one way to understand the sum of squares method for solving problem number 1 is to actually think of it as approaching this problem by actually finding a certificate of non-negativity. So it will try to decide if, F is non-negative on the hypercube by finding if there exists a certificate of non-negativity of F, okay? And in some sense, this brings us to, our first main idea, which is, the kind of certificates that this algorithm is going to search for, okay? And so I'll suppress saying of non-negativity because that's what I'll always mean by certificates. So I'm just going to sum of square certificate or SOS certificate for F means SOS certificate of non-negativity for F. It means the following, okay? So here's the definition. A degree D SOS certificate of non-negativity of F. So F is still, a polynomial over the hypercube. So let's call it is a list of polynomials. Let's say G1 up to G sub R, also on the hypercube. Each GI has degree at most, let's say D over 2, and fx equals sum over I at most R, gi of x square for all x in the hypercube. Okay, so just to parse this statement out, I said that I'm looking for certain kind of certificates of non-negativity. Okay, and in particular I'm going to be interested in certificates that can be verified quickly if somebody hands them over to you. So in particular, the sum of squares algorithm is going to look for sum of squares certificates of non-negativity, and they are described by a list of polynomials. If I'm going to call, trying to look for degree D certificate, then each of these polynomials G sub I would be of degree at most D over 2. And this polynomial identity fx equals sum I gi squared should hold over the hypercube. Okay. So G1 through GR I'm going to call that a degree D SOS certificate of non-negativity of F. Okay. So first of all, let's understand if this is sensible, right? Like, is it sensible to call this a certificate as in the definition? Suppose F satisfies this identity. Suppose, there exists a degree D SOS certificate of non-negativity for F. First, we should check if F indeed is non-negative in that case. But that I think is obvious, because each of the polynomials that appears on the right-hand side is a square. It's clear that this representation immediately tells you that F is non-negative, right? So if somebody convinced you that F indeed equals sum gi squared, then clearly F is non-negative over the hypercube. You all agree? Good. So also, I guess maybe a note about terminology. People tend to also use the word, let's see, proof for certificates. And that means exactly the same for us. So an SOS proof of non-negativity is exactly the same as SOS certificate of non-negativity. Okay, good. So, so I guess, I said I'm going to be interested in certificates which are efficiently verifiable. So I guess the first question to ask is, why is this certificate efficiently verifiable at all? Okay, why is the degree D certificate, if it exists, efficiently verifiable? I guess the first thing to understand is, so remember I had R polynomials. So if the certificate is going to be efficiently verifiable, and remember we are looking at, like, the notion of efficiency is polynomial time in the size of the input F. Okay, so we are looking for efficient algorithms where the running time of them, etc., is polynomial in the representation of F. So, polynomial in, for example, the sum of the bit representations of the coefficients. Okay, so for this to be possible, we first have to control the number of polynomials GIs in the list, right? So the number of polynomials in the list for R, if R happens to be very, very large, like let's say 2 to the n, then certainly there is no way that I can verify that certificate efficiently in the measure I'm interested in, right? So I guess the first question that you encounter when you talk about this is, how large is R? So we can actually prove in about 10 minutes that actually whenever there is a degree D certificate of non-negativity of F, we can actually take R to be at most n to the D. Okay, so that's one hurdle solved. We can at least assume that R is not too large. The second question we might be worried about is, so we know that there are only n to the D or less number of polynomials GIs, and each polynomial GI was of degree D over 2. So I can certainly describe this whole list in like polynomial in n to the D size, if the bit representations of the coefficients of GIs are small, right? So I also have to worry about how large are the coefficients of GIs. So even if the polynomials are few in number and they are low degree, if their coefficients are very large, then this certificate, will not be efficiently representable. So definitely not efficiently verifiable. So these are the two questions that we are obviously, going to encounter in even trying to justify whether this certificate is efficiently verifiable. Let's, table them for a bit. Okay. Let's first check that if at least these two hurdles don't bother us, then we are done. Okay. So here's a proposition. Suppose R is at most n to the d, and all coefficients of GI are bounded in magnitude by 2 to the polynomial in n to the d. So notice that if an integer number is bounded by 2 to the polynomial in n to the d, then its bit complexity, the size of that number, the number of bits you require to write it down, is going to be polynomial in n to the d. So we are happy about it. So suppose R is at most n to the d, and suppose all the coefficients of GI are bounded. So they're rational numbers where the integers appearing in them are at most 2 to the polynomial in n to the d. Then the identity f equals some GI square over the hypercube can be checked in polynomial time. Okay. So once I prove this proposition and once I justify these two questions above, then at least I have given you an argument for why it is legit to call sum of square certificates efficiently verifiable certificates of non-negativity. Okay. So let's quickly see a proof of this proposition. It's kind of unfortunate. I don't have enough screen real estate to hold both the theorem and the proof together. So we're going to make do with this, I guess. Let's see. Let's try to at least keep some part of it. So, I mean, this is essentially, an exercise in verification. So let's just, run through it. So you're given GI and its coefficients are, polynomially bounded. Once you are given such a GI, so remember all these GIs are also given to you as polynomials in the coefficient vector representation. So you basically get each of the coefficients given to you. Each coefficient is a rational number, and it has polynomial bit size. So these GIs are given to you. I claim that given such GIs, you can compute GI square in polynomial time. And that's not that hard to see. So hopefully you're convinced of that. Once I'm done with that, I claim that you can compute some GI square in polynomial time. That's also not that hard to see. Once GI squares is in your hand, you can, there are only n to the d of them, like R is at most n to the d. So I can compute some GI square, in particular the coefficient vector representation of this new polynomial in also polynomial in n to the d time. Good. And so now, my task becomes to check if these two polynomials, some GI square and f, are equal. Okay. So in particular, I'm trying to check whether this polynomial is 0 for all x in the hypercube. Okay. So here I'm going to use a fact, and it would appear in one of your homeworks as an exercise. It's a very simple fact that I'm going to use. For all f, a function of the hypercube, there exists a unique representation of f as a polynomial. So in particular, there is a representation of f hat s product I in s xi, just the polynomial coefficient vector representation, as I said. And in particular, this is saying that coefficient vector representation is unique. So there is only one way to write f as a multilinear polynomial over the hypercube. Okay. And some of you might have seen this before. This representation of a Boolean function is actually just this Fourier transform. And actually, just using very basic properties of Fourier transform, very elementary properties, actually easy to prove that this representation exists and is unique. I'm not going to prove it right now. If actually, it would be on your homework, so that way, we'll be sure that we have actually seen the proof of it. So one point I want to remind you though, so far, when we were given polynomials, we were not assuming that they were multilinear. By the way, just to remind you, multilinear means that every monomial that appears in the representation of the polynomial, the degree of any single variable like xi in it is at most 1. Okay. So for example, there is no term like xi square that appears in the representation of f. And why can I intuitively assume that such a representation exists? Well, remember, over the hypercube, xi square is always 1 because xi takes the value plus or minus 1. So in some sense, whenever xi square appears, you can, just without loss of any generality, strike it off and replace it by 1. This process of, taking squares of variables and killing them and replacing them by 1 is called, multilinear reduction. If you just do it repeatedly, then you will end up with a multilinear polynomial representation of f. What this fact is saying is that this representation is going to be unique, that there are no two different ways to write the same polynomial as a multilinear polynomial. Okay. So in particular, if you do multilinear reduction on a polynomial over the hypercube, you're going to get a unique representation as a multilinear polynomial. And that actually, helps us complete the proof of this verification, because, we were trying to check whether f and some gi square are equal over the hypercube. So we take some gi square and we run multilinear reduction on it. So we replace, whenever we take a monomial, whenever a variable appears with a degree bigger than 1, then, we can just write it as we can write the degree of it as some even number plus, if it, so maybe I can write it down. Let's write it in yellow. So, if I have, let's say, a monomial like xi to the 10, xj to the 5, then by multilinear reduction, I can just basically replace xi to the 10 by 1 and xj to the 5 by xj. And so, the resulting thingy is a multilinear monomial. So just, run this multilinear reduction procedure on some gi square. You'll end up with a multilinear polynomial. Same thing, same procedure on f. You end up with a multilinear polynomial. And now, because the resulting polynomial f minus some gi squared is a multilinear polynomial, the only way it can be 0 over the hypercube is if all of its coefficients are 0. This is basically, a consequence of uniqueness of representations. That you cannot have a polynomial with non-zero coefficients take value identically 0 over the hypercube. Okay. Good. So that's, a simple proof that shows that, at least if R is small and all coefficients of the polynomials gi appearing in our proof are not too large, so, they're bounded above by 2 to the polynomial n to the d, then we can efficiently verify the identity f equals some gi squared. And in particular, we can convince ourselves that f is non-negative over the hypercube. Any questions at this point? Okay, very good. So, good. There is my scrambling for my notes over here. Okay, very good. So I want to justify these two claims to you. Why can we take R to be small, and why can we somehow argue that the bit complexity of the coefficients of GIs cannot be too large? But before that, I want to show you something very simple. Okay, I can show you, some kind of completeness of this way of finding certificates. So what I mean by that is, I'm hunting for a very special kind of certificate of non-negativity. One of the things you might be bothered by is, why should there be a certificate like this at all? Like, in some sense, is this like a complete procedure? Can I always find a certificate of this form if my function is non-negative? Otherwise, in some sense, I'm strictly limiting myself. And so I want to prove a proposition, which is that let f minus 1, 1 to the n to the r be non-negative over the hypercube, then there exists a degree 2n certificate of SOS certificate of non-negativity of f. So, this is, as we'll see, in some sense, degree 2n is quite bad. In some sense, it will amount to exponential time algorithms once I tell you about algorithms. But at least this is telling you that, this system of finding certificates of non-negativity is complete. At least whenever you look for it, there is one. It might be of prohibitively high degree, but there is one. Okay. And so this is saying that for every non-negative f, there is a way to prove it non-negative by means of a SOS certificate where the polynomials that appear in it are of degree at most n. Okay, good. Let's prove this. It's very simple. So consider, the following polynomial. Describe where, where gx for every x equals square root of fx. Okay. So the value of g at any x is just the square root of the value that f takes. Okay. Now, the only thing we are going to use is that every function on the Boolean hypercube is a polynomial of degree n. Why is this true? Well, this again follows from uniqueness of multilinear representation that we used in the previous proposition. The multilinear representation, precisely because of being multilinear, cannot have a monomial of degree bigger than n. And so, the same fact that we used in the previous proposition and which you will prove on a homework shows that every function is a polynomial. Every function on the Boolean hypercube is a polynomial, of degree at most n. So g itself is a polynomial of degree at most n, which means that I can write f as g square. G is of degree n, so g square is of degree 2n, and so this is basically a degree 2n SOS certificate. Okay, short and sweet, very simple. So at least there's always an SOS certificate of non-negativity. Good. Oh, and I guess okay, I'll do this first and then prove that. Good. So let's go ahead and justify these 2 points that I left behind when we were proving this issue of efficient verifiability. And there's actually a cool fact that goes into it. In fact, that fact we're going to rely on a whole lot of times. So let's get into it. Oh no. Okay. So first, I just want to remind you of a piece of notation which is going to make my life very simple. It's a tensor notation. So if you have a vector v in Rn, then v tensor to the 2, let's say, is a vector in Rn square. Okay. And you should think of it, you can think of the coordinates of v tensor to the 2 as indexed by all possible pairs, ordered pairs of coordinates of v. Okay. So coordinates are indexed by ordered pairs I comma j, and the I comma jth entry of v tensor to the 2 just equals vi times vj. Okay, so in some sense, it's a way to write down all possible degree 2 monomials in v into a vector. Okay, and notice that the monomial vi vj appears twice, once as ij and once as ji. In a similar way, I can actually write down larger tensor powers. So v tensor k is going to be a vector in Rn to the k, is going to be indexed by ordered k-tuples of integers from 1 through n. And just like v tensor to the 2 is going to be the product of the coordinates that appear in that index. Okay, so let me write like this. Or actually, let me not define it because it'll take a lot of time. But you understand what V tensor to the K means. The other thing I'm going to use, this is simpler, is, given a vector V, I'll form an n+1 dimensional vector by appending 1 to the first coordinate and write 1 comma V for this n+1 dimensional vector, okay? So this is basically the vector where the first coordinate is 1 and, the rest of the n coordinates are basically the coordinates of V. Okay, good. That's just, some piece of notation. Good, very good. And let me also remind you of a fact that if you already did homework 0, then you already know. Otherwise, we're going to take it as a fact. Once you do homework 0, it will become a theorem for you. So we defined positive semi-definite matrices on the homework. And, one condition that we proved as an equivalent condition to being positive semi-definite for a matrix A is that there exists a matrix B such that A equals B transpose B. Okay. So I'm going to take this as a fact. I'm going to assume that you know how to prove this, or at least know the truth of it. Good. So notation, fact, and now, I can tell you this theorem that I've been building up to. It's a very simple theorem, but quite nice. So let's title this as PSD matrices versus SOS certificates. We basically are going to show a correspondence between PSD matrices and SOS certificates of non-negativity. And in some sense, this is somehow the key connection between semi-definite programming and, sum of square certificates and all that jazz. So remember F, it's always going to be a Boolean function. F has degree D certificate, SOS certificate of non-negativity if and only if there exists a matrix A such that A is positive semi-definite and Fx equals 1x, the vector n+1 dimensional vector made by appending 1 to x. Take d over 2th tensor power of this vector. Okay, if you haven't seen this notation first, it can appear daunting, but it's actually very simple. So let me convince you of that, okay? So what's going on here, let me parse it for you, okay? 1 comma x, I guess I can use this. 1 comma x is the n+1 dimensional vector. We are taking a d over 2th tensor power of it, okay? Here is a way to, understand what's going on. This is a way to populate in a vector all possible monomials in the variable x of degree at most d over 2. Okay, so I claim that for every monomial of degree d over 2 or smaller, you actually have a corresponding entry in this big tensor. And in some sense, that's the reason I appended 1 to it. If I just took the tensor power of x instead, then I will only get a vector whose entries are going to be all possible homogeneous monomials of degree d over 2. I'm actually interested in getting monomials of degree d over 2 and smaller, and this one appending is just a trick to get that. Okay, so convince yourself that this tensor power has entries which are just monomials of degree at most d over 2 in x, and in fact all possible monomials appear. Some appear multiple times. Good. So this matrix A lives in this. So what space does this matrix live in? This matrix lives in R and n+1 to the d over 2 times n+1 into the d over 2. Okay, by just notation that we just discussed. Okay, and so what am I saying? I'm saying that fx can be represented as just inner product of two vectors. One of them is just the monomial vector. The other is the monomial vector on which I have applied this matrix A. Okay, so let's prove this. Let's erase this part. By the way, feel free to stop me, okay? Like these are all basic things, but notation can be somewhat confusing. So feel free to stop me if I am saying something that's not clear. Good. So let's prove, the if part. I'm going to just do very basic linear algebra to prove this. So remember that A equals B transpose B for some matrix B, because A is positive semi-definite. So, I can write, so 1 comma x d over 2 B transpose B 1x d over 2. And now, I'm just going to take the adjoint of, like, I'm just going to, like represent, I'm just going to take, the adjoint representation. So I'm just going to like move this B transpose around on the other side. If you remember, you're basically in algebra, once I take B transpose on the other side, it becomes, transpose of it. So this actually equals, by basic linear algebra, this B is basically transposed of B transpose, which equals B. Okay, so what we've written down is basically, a claim that fx actually can be written like this. And if you look at this, this is some vector. It's b times, b applied to some vector. The same vector appears on the right hand side. So this is inner product of a vector with itself. If you remember, this is actually equal to the square of its L2 norm. So this basically equals b 1x d over 2 L2 norm squared. Good. So we've just arrived at, like, this representation of this f. And now, if you look at, if you remember, what L2 square norm looks like, then, it's just the sum of the squares of, the entries of the vector, right? So let's, write down gi for the ith coordinate of this vector. Again, like the notation can be daunting. We'll go over it again, but let me just run you through it one time first. So look at this vector. This is a vector in n plus 1 to the d over 2 dimensions. So I will run, from 1 up till n plus 1 to the d over 2. And let's call gix, the ith entry of this vector, which I can represent as the inner product of, the standard basis vector e sub I times b1x to the d over 2. And lo and behold, we basically have so the reason I can write it as gix is because it's a polynomial of degree at most d over 2. B is a matrix of constants. It's applied to this vector of monomials of degree at most d over 2. So gi here is actually simply a polynomial of degree d over 2. Okay. And what I just reminded you was that this is the L2 square norm of it. So it actually equals the sum of the squares of the coordinates of it. So that means that fx actually equals sum I from 1 to n plus 1 to the d over 2 gix squared. Okay, so what have we proven? We've proven that if f has a representation of the form in the claim here, then in fact f must be a sum of squares. Okay, so because it was notation intensive, I'm going to pause for like 30 seconds. It's always simple, but it's just intensive notation. And take any questions if you have. I don't know where to stop, I guess here. Let's see.
So the redundancy in the set of monomials, it's not actually necessary, right? Like it's just for the convenience of notation.
Yes, absolutely. Yes. Yeah, there is a way to define, define a vector where every monomial appears exactly once and everything would work perfectly fine and you would save some constants. But we are, there's so much water under the bridge of these polynomials here. It's like we've given up on optimizing constants for now. And again, the proof is nicer in this notation. So yeah, you're right. Absolutely. It's only a notational convenience to use this tensor business.
Okay, thanks.
Good. Very good. So we've proven the if part. Let's prove the only if part. So, what does only if mean? Suppose that f has some SOS certificate. Well, what does it mean? It means that f can be written as sum of some gi squares, let's say r of them. right? Now, here is, the only thing I'm going to use. And in some sense, I'm going to use this kind of trick again and again and again. It's very simple, but once you see it, you can use it again. Maybe it's confusing for the first time. So every polynomial can be written. So, if gi is a polynomial, then gi can be written as inner product of some vector v with, this monomial tensor. And because of the redundancy, because of the fact that the same monomial appears multiple times in this vector on the right, there are multiple vectors that will serve the job, but any one of them is fine. So any polynomial can be written as inner product of a vector of constants. This vi actually depends only on the coefficients of g sub I, with, this d over 2. So this is d over 2 degree. That's why I wrote it in that form. So any polynomial of degree d over 2 can be written, as the inner product of some vector vi with 1 comma x to the d over 2. Okay. And if that's true, then, fx, equals some I vi 1 comma x to the d over 2 here square. And now, I'm just going to do basic linear algebraic manipulations again. So I'm going to write this as some I vi transposed. Okay. Let's bound my left bracket over there. Let's see. Okay. And this is basically an algebra, like nothing very fancy going on here. I'm literally taking this square representation, and writing it, taking out this matrix here, like which is the matrix of some of the outer products of these vi's, and writing down this expression in this form. And I'm going to claim once I've done this, I'm actually completely done, because by what you were supposed to have proven in homework 0, some I vi transposed is always a PSD matrix. Okay, so any PSD matrix, in fact, can be written as sum of outer products, and sum of outer products is always positive semi-definite. One way to prove that is to verify that if you take any quadratic form of such a matrix, then it's a sum of squares and therefore non-negative. And so you know that a matrix is PSD if and only if it's all its quadratic forms are non-negative. And all of this you were supposed to have done on homework 0. So I'm going to assume that nothing is a problem here. I'm kidding. I can take questions. Okay, good. Yeah, this was simple. Very good. So one immediate corollary of this, which some of you might already have observed, is that we have actually crossed the first issue that we encountered when we were proving efficient verifiability of such certificates. Okay, we have proven, I claim, that if F has a degree D certificate, then in fact it has a certificate with R at most n to the D over 2. So let me pause and let someone else tell me why this is true, because I claim that this is like a one-line corollary of what we just proved. This is an interactive segment of our Zoom call. Who wants to tell me a proof of this?
Is this just the rank of B? Or rank of, yeah.
Yeah, exactly. Yes. So, we can go back to our, so we actually constructed a very explicit representation, right? If you go back to our proof here, so let's maybe reason it this way, okay? F has a degree D certificate. By applying this theorem, we know that F in fact can be written as, inner product of this 1x tensor to the D over 2 times A times 1x to the tensor to the D over 2. Here A was a n plus 1 to the D over 2 by n plus 1 to the D over 2 matrix, right? And then we, took this matrix and explicitly constructed a SOS representation for F, where the number of polynomials appearing in the representation were equal to the number of coordinates in this vector, which is at most n plus 1 to the D over 2. Okay, so I guess I am a little bit wrong there. Not n to the D over 2, n plus 1. to the d over 2. But hopefully that's convincing, very simple. And so we've at least proven that if there is any degree D certificate, then in fact there must be one with at most n plus 1 to the d over 2 terms in it. So that's good. The bit complexity bit is still remaining. So let's handle that next. And so let's call it bit complexity of SOS proofs. So suppose F has a degree D SOS certificate over plus minus 1 to the n, then actually okay, let's see. I think I can prove that F has a degree D SOS certificate with bit complexity polynomial in n to the d. So before proving this lemma, or actually I'm only going to sketch and leave some of the details out to you. You'll see that in fact such kind of results are not exactly piece of cakes. They are kind of non-trivial. And so I'm going to sketch this proof out of you, but leave some details out for you to fill in. But before that, I want to mention a big caveat. This is a lemma that I am only stating for the hypercube right now. We will go to more general SOS proofs very soon and discuss, polynomial feasibility problem that we talked about earlier. Such a lemma actually in general is not true. It's actually, for the hypercube, in some sense, we are in a somewhat special situation. That's why it turns out to be true. In general, just the existence of a low degree certificate doesn't imply that there is one where, you can bound the bit complexity in by some natural function of n to the d. In fact, you can give examples where even though there is a degree 2 certificate of non-negativity, every degree 2 certificate must have bit complexity which is like exponential. And so these bit complexity details can be really tricky. We are getting lucky in the hypercube that we don't have to worry about it. Okay, that's what this lemma allows you to do. But I guess my disclaimer is that this is not in general true. If you go across other domains, it's not going to be true in general. Okay. Again, I'll provide some references on Diderot to tell you about all kinds of weird things that go on with SOS proofs, and so in particular examples where bit complexity can be unbounded, etc. Good, but let's sketch a proof of this. So we are going to use this theorem that we just proved, which gives you an equivalence between low degree SOS certificates and PSD matrices. So we can write fx as 1 comma x tensor to the d over 2 times for some matrix A. And the issue is that a priori we don't quite know how large the entries of A might be. For all we know, the number of bits required to write down the entries of A could be unbounded, or could have very large number of very large bit complexity. So this representation by itself does not tell us whether F has a small bit complexity SOS proof. Peter, is there a question?
Yeah, Ines just had a question. He asks, can you trade off degree and bit complexity for certificates not over the hypercube?
That's a good question, and it turns out that the answer is no. So it turns out that all these results are actually somewhat non-trivial, and even in very simple situations. For example, the following is known: there is a very explicit, very simple degree 2 system of polynomials for which there is a degree 2 certificate of non-negativity. But and the bit complexity of any degree 2 certificate is high, and in fact you can prove that the bit complexity of any degree less than or equal to square root of n, where n is the number of variables in the system, any degree less than or equal to root n certificate is also exponential. And so so in general you can't hope to fix this problem by just increasing the degree let's say by a constant factor or something. This is a real problem. It's not something that we can circumvent in general. Any other questions, I guess? Ah, I actually don't know which result you're talking about, Daniel. Is this result true for other sets, say R? Can you remind me what you're talking about here? It's about half an hour old. I'm so sorry for not looking at this earlier.
No, don't worry. It was about the result on the hypercube.
Okay.
That said that you always have a certificate, and it's a certificate for positivity. But someone
Yes.
already told me the Motzkin polynomial is a polynomial which has no certificate.
Yes, it's an excellent question, and the answer I want to give is a qualified yes. Actually, so it's true that Motzkin doesn't have a certificate, and in some sense, the way you can actually get into a situation where you at least always have some approximate certificate is by restricting yourself to domains that are what are called as explicitly bounded. And so basically it means that the constraint system somehow derives that the norm squared of, let's say, every point in the set is bounded above by some small number. So for example, in the hypercube, you can derive that sum of xi squared equals n. And so the hypercube is a explicitly bounded domain. So in general, other domains also satisfy this property. For example, let's say you are trying to find positivity certificates over the sphere, which is like the set where sum of xi squared equals 1. That also is an explicitly bounded domain. And it turns out that in such situations, you can get approximate certificates. Again, I'll define and discuss this in more detail, maybe 4 lectures down. It's true that if you have unbounded domains, then things can go. In general, there's no guarantee that such certificates exist at all. And Tim already gave you one example. And again, we'll see that example too, actually, somewhere down the line. Good. Very good. So coming back, we were trying to prove this bit complexity or sketch this bit complexity lemma. So we said, F has a degree D certificate. So F can be written like this. And our worry is that A can have, entries which may not have, a small size at all. And so a priori, this representation does not give us anything, right? So let's try to argue about what entries of A might look like to, help us out here. So the point, is that I can, so, let's try to understand what the coefficient of some multilinear monomial U might look like on the right-hand side. So F has a coefficient representation. Remember, F looks like sum over U, F hat U, XU, right? Where XU is just, product of singletons in U. And these are all multilinear monomials, remember, because we are looking at, only multilinear polynomials when we're looking at hypercube. So what I want to understand is, what does F hat U look like in terms of this representation on the right? And so, it's actually not that hard to convince yourself that it actually equals so the notation is a bit jarring. So let me again, explain to you what's going on. S and T are, ordered k tuples, or sorry, D over 2 tuples. But when I'm taking their symmetric difference, I'm thinking of them as just the sets that they describe. Okay. And when I'm talking about their size, I'm again thinking of as just the sets they describe. The other way, the right way to do it will take me like 5 minutes to set up notation for something that's not worth it. so hopefully you'll bear with me here. So S and T are ordered tuples, so A's entries are indexed by this ordered D over 2 tuples. And so I'm claiming that F hat U equals the coefficient F hat U equals the sum of the entries of A at S comma T, where S and T are k tuples whose sets have a symmetric difference equal to U. Okay, and this is simply using the following idea that if you look at the monomial XS and monomial XT, okay, then if you expand this, quadratic form out here on the right, if you expand this quadratic form, then, you're just going to get sum like this, AST sum over ST. Okay, that's how this quadratic form expands out. And the observation is that XS times XT, when you do multilinear reduction, equals X of S delta T, or symmetric difference of S and T. And so, basically we are collecting all terms where the corresponding product of the two monomials, symmetric differences out to the monomial we are concerned about, U. Okay, and we're just adding them up. So that's what the proof of this is. And well, some sloppy board work here, virtual board work. Okay, very good. And so what does that buy us? So in particular, if you look at the empty coefficient, the constant term in the polynomial, then you get that it equals s sum over s of ASS. So it's just the sum of the diagonal entries of the matrix A. Okay. And again, if you did your homework, then you know that the sum of the diagonal entries of a matrix is its trace. So we've just proven that the empty coefficient of F equals the trace of A. Very good. Again, if you've done your homework, and if I remember to put this question on the homework, hopefully I did, then trace of A is the sum of its eigenvalues, basic facts from linear algebra. And remember, eigenvalues of A are non-negative, so lambda i's are all non-negative. A is PSD. Very good. So what have we just proven? We have proven that F hat phi equals trace of A equals sum of the lambda i's. And now, we assume that in some sense, the input size is, the size of the coefficients of F. So in some sense, we are trying to bound the bit complexity of entries of A in terms of the entries of F. So in particular, we can assume that F hat phi has like polynomial bit complexity, which means that some of the eigenvalues has polynomial bit complexity, which means that each eigenvalue must have polynomial bit complexity because these are all non-negative numbers here. Good. So far, so good. And what that means is that, another exercise I'm going to use from the homework is that the sum of the entries of the matrix A, some of the squares of the entries of the matrix A is what is called as its Frobenius norm, square of its Frobenius norm. It also equals the sum of the squares of its eigenvalues. And, we can use the Cauchy-Schwarz inequality to bound this in terms of some lambda i's. And so, this chain of inequality proves that I can bound the Frobenius squared norm of the matrix A by something which is polynomial in the size of F, in particular size of just the empty coefficient of F. Good. So what have we proven? We actually just established that if F has such a representation, then in fact A's entries cannot be too large. Like A's entries are in fact, bounded. Okay, bounded with some polynomial blow up, if at all. Okay, that's good. That doesn't still prove that I can find squares whose coefficients are small. So, from here, is the sketchy part, which I'm going to tell you everything, but then send you references and some guidelines on how to prove it. So there is an algorithm for taking any matrix A and doing what is called as an LDL transpose decomposition. This is not the eigenvalue decomposition, and there is a good reason for it. In some sense, we want to do some decomposition where I don't have to take square roots, etc. And so this LDL decomposition, D is a positive diagonal matrix, and L is what is called as a triangular matrix, meaning only entries of its lower triangular parts are non-zero, and its diagonal entries are unit, meaning they are all one. So it turns out that every matrix has such a decomposition, and you can compute it in polynomial time in the size of A, including its bit complexity, for example. And it's not exactly trivial how to do this. So I'm going to give you a paper to read on how to do this if you're interested. But basically you can do this. And once you have such a representation, once you have such a representation for A, you can actually use it to generate sum of squares representation that has small bit complexity. And the idea for that is to take this representation that we had and replace A by LDL transposed. Then do the adjoint business again move L transpose on the other side. And now, you have to remember that, you're taking inner product of two vectors, and the entries of the second vector are just going to be scalings, of the coordinates of the first vector. And so, this representation, in fact, is already a SOS. Okay. So not exactly trivial. It relies on a cool fact and not so simple to prove fact of this LD-L transpose decompositions. But, this is not a linear algebra class, so we're not going to prove this. Instead, I'm just going to give you references on, Diderot for why this exists and why it can be computed. Good. So that was the proof of this fact that, if F has a degree D SOS certificate over the hypercube, then in fact it has one which has small bit complexity. And, I gave you the disclaimer, which is that this is a very special fact that happens to be true for hypercube. It's not in general true for other domains. Good. So that's 5:33. We're going to take a 10-minute break. We're going to return at 5:43 to continue. Okay. All right. To take a break because we're going to shift gears now and, ask the question, what happens when there is no certificate of non-negativity, for a function f? So what happens when f does not have a degree D SOS certificate? Now, we already proved that if f is non-negative, then it must have a degree 2n certificate, right? So one way that f may not have a degree D SOS certificate is by simply, not being non-negative. There exists an x such that fx is less than 0. But when D is much less than 2n, f may fail to have certificates of non-negativity of degree D, even when it is always, non-negative.
Oh, hey, Pravesh, you should share your screen, by the way.
Oh, thank you. I have been writing to myself, I guess. Good catch. Wait, iPhone, iPad via cable. Good. Sorry about that, and thanks, Peter. Yeah, so we are wondering, what happens when f does not have a degree D SOS certificate of non-negativity. And, we discussed that when, one way this can fail is, if there is an x where f is negative. If f is not non-negative with a hypercube, it certainly won't have certificates of non-negativity. But when D is less than 2n, then in fact, f may be non-negative, and yet there is no certificate. Okay. So now we want to analyze, what can we say? And we are trying to, what we're going to do is, develop some duality theory of, some objects that exist when f does not have a certificate of, non-negativity. Like in some sense, our hope is to, get at this point, find an x where f is negative. Like ideally, what we would like to say is that if f does not have a degree D certificate of non-negativity, in an ideal world, f should not be non-negative, and therefore there should be an x where f is non-negative, f is negative, and then a natural algorithmic question is to just find that x. Okay. And so, in some sense, we are going to develop some duality theory to somehow, help us understand to what extent we can actually do that. See, there are some chat messages. Whoa. Okay, not sure what happened. Are there any questions, Peter? Like, do you see any questions in the chat by any chance?
No.
Okay,
Last message I see is from like 242.
Okay, great. So it turns out that when f does not have a certificate of non-negativity of degree D, we actually will show that there is an object with a really nice fancy name that exists. And we're going to call it a pseudo-distribution, and I'm going to justify to you why it's called that way very soon. Okay. So let's try to reason before like giving you a formal definition. Let's try to reason what happens, in this case when d is much smaller than 2n. So here is a fact that's actually not that hard to prove, and your homework kind of equips you to prove these kind of things. So consider the set of all f such that f has a degree d certificate of non-negativity. Okay, so take all polynomials which are not only non-negative over the hypercube but also admit a degree d SOS certificate of non-negativity. Then this set is a closed convex cone. Okay, all these terms were defined, and like some at least aspect of what they mean was given to you in the homework. I guess it's kind of assumed to be a prerequisite that you know this, but let me at least define it for you. Okay, so a set is convex if for any 2 points that lie inside the set, the segment joining them also is completely contained inside the set. Okay, and I'm sure you've seen convexity in some form before, so it's not so hard to observe that this set f is convex. Okay, why is that? Well, if f, let's say f1 and f2 are have degree d SOS certificates of non-negativity, then just any convex combination of them would have an SOS certificate too, just by taking convex combinations of the polynomials that appear. Okay, make sense? So in notation I'm saying that if f1 equals, let's say, some gi squared and f2 equals some, let's say, hi squared, then for any alpha in 0 1, alpha f1 plus 1 minus alpha f2 equals alpha, and alpha is non-negative, so I can write it like this. So that's the SOS representation for a convex combination. That proves to you that this set is convex. It's a cone because it's basically it contain if f is present in it, then any non-negative scaling of f is also present in it. And convex sets where which are closed under taking non-negative scalings are called as convex cones. So this is a convex cone. And the last fact that's we need is that this is a closed set in terms of with respect to the usual topology. In other words, what I mean is that from our perspective, when you think of it as the following, that if you have a point which is arbitrarily well approximated by points in the set, then in fact the point itself must be in this set. Okay, so if you have some function g which is for any epsilon, you can actually find a function which is closed within, let's say, Euclidean distance to it, then g itself must be inside the set. So don't want to harp on this too much, but basically this is a closed convex cone. And now what we're going to do is rely on an exercise that you hopefully solved in homework 0, which is the separating hyperplane lemma. So let me remind you what that is. It's actually a fundamental theorem of convex analysis. It tells you that if, let's say, K is a convex set, which is closed, and guess we also need bounded, but let's just not worry about it too much right now. And we have a point, let's say V, which is not in this set K. Then on your homework you proved that in fact there must be a hyperplane, a half space actually, which is basically the set described by all points x such that ux is, let's say, non-negative for some normal vector of the half space U, such that all of the convex set is contained inside H while V is not in H. So in other words, there is some hyperplane such that this point V, which is not in the convex set K, lies outside, like lies on one side of the hyperplane, while the whole convex set K is contained on the other side of it. Okay, so actually let me, because I'm not stating a theorem, let me just continue like this because we are still in the discussion mode. So, okay, so what have we learned so far? Well, we have a closed convex cone. of all polynomials that have a degree D SOS certificate of non-negativity. And we are trying to reason about what happens when a certain polynomial given to us, let's say P, is not in this cone. So let's maybe give this a name. Let's call this, SOSD. Okay. So we're now trying to understand what happens when P doesn't belong to SOSD, right? Well, we can apply hyperplane separating lemma, like this lemma that we just discussed, and conclude that there must be some vector, let me call it mu. You'll see why in a second, but there must be some normal vector mu such that the half space defined by mu has SOSD on one side of it while P on the other side of it. Okay. So far so good. Yeah, I mean, please feel free to ask questions, if there's anything confusing going on. So before talking more about this hyperplane, let's try to understand what does it live in. Where are we? Like what is the space that all these sets are living in? So remember, f was a function of the hypercube. Any such function, basically can be described by all its values on the hypercube. So you can simply think of this as a 2 to the n dimensional vector, the vector that populates all possible values of it on all possible points on the hypercube. So we are basically thinking of this set as a subset of R2 to the n. Okay. And so now what we are saying is that if some function, some polynomial P does not live in this set, right? Then because this set SOSD is a closed convex cone, there must be a hyperplane that separates P from it, right? So the hyperplane must also live in the same space as, this F. So in particular, I can think of it as a function on the hypercube. Good. So we just saw that, the normal vector is basically, represented by, can be thought of as a function on the hypercube itself, right? And what does this inner product mean? So inner product, in this space basically looks like, for any f, we can think of mu dot f as simply sum over x in the hypercube of fx times mu x. Okay, good. Now the only other thing I'm going to do is, without loss of generality, I can scale mu so that its entries sum up to 1. Right? So far so good. So what do we have here? We must, in some sense, in this somewhat vague and informal discussion, we've concluded that if P does not have a SOS certificate of non-negativity, then there must be a mu, a Boolean function, such that its entries sum up to 1. Sum over x in the cube, Px, is less than 0. And sum over x, mu x, fx, is bigger than or equal to 0 for all f in SOSD. Still following? Make sense? So, this notation almost at this point demands that you ask the following question. What happens if all the entries of mu are non-negative? If for whatever reason, this hyperplane, the normal vector to the hyperplane, happen to have only non-negative values, what does that mean? It means something nice. So let's, try to explore that. In that case, so let's try to, if mu is non-negative, then it describes a probability distribution over the Boolean hypercube. Yeah. And in that case, I can use some very nice notation for, these inner product thingies here. So I can write, for example, this as the expectation with respect to mu of the function P. And I can write this as expectation with respect to mu of the function f. And so in this case, this special case, which we are essentially just dreaming of right now, what we are saying is that there exists a distribution such that the expectation with respect to it of the function p that did not have a certificate was negative, while for all f in SOSD, expectation f is bigger than or equal to 0. Okay? And so, basically, if you think a little bit more about it, if you have any function which is non-negative on the hypercube, whether it is an SOSD or not does not matter. For any distribution, this inequality is going to hold. If I have a function which is always non-negative, then its expectation with respect to any distribution must be non-negative. So this is not a surprise at all, right? And what this is saying in particular is that, P, there must be a distribution under which the polynomial P that did not have a SOS certificate of non-negativity has a negative expectation, right? In particular, it must mean that there must be an X for which P is negative, right? Otherwise, this would not have been possible. So in general, what have we arrived at? We have arrived at some kind of a dual description of what happens when, a polynomial P does not have a degree D certificate of non-negativity in terms of, this mu, which, at least when it is all non-negative, we, like to think of it as a distribution. Now, of course, in general, mu need not be, non-negative at all, but it turns out that it shares some very interesting and useful properties of an actual distribution, okay? And so in some sense, what we're going to do now is define this separating hyperplane, the normal vector to the separating hyperplane that arrives here. We're going to call it a pseudo-distribution and explore a few of its properties. Okay, that's what our goal is next.
Pravesh.
Yes.
Quick question.
Yeah.
Why is it the case that you can't have sum of x mu of x is equal to 0?
Good. Yeah. So I have not actually established mu, the properties of mu, etc. at all here. It's a good question why sum x mu x cannot be 0. And when I prove the duality theorem formally, I'll prove to you that in fact cannot happen. It's a very good question. And so hold that for this informal discussion. Yeah.
Okay.
Good. Very good. Yes. In this case, the threshold happens to be 0. So let's formalize this discussion and do something interesting with it. But before that, I'm going to set a notation. In some sense, it's a key notation for us in this course. And so I'm going to title it, and I'm going to call it pseudo-distribution. Actually, I'm only defining the expectation aspect of it. So I'm going to call the pseudo-expectation. So we're going to use this notation to simply denote these inner product like quantities we were working with, even when mu is not non-negative, okay? And to remind ourselves that, there might be something funky happening because mu is not non-negative, we put like a little twiddle, on top of E. So this E twiddle is read as a pseudo expectation. In some sense, we are using suggestive notation in order to, motivate ourselves to prove properties that might hold for distributions, even for pseudo distributions to the extent possible. And so we are going to use this E twiddle notation to remind us of this little discussion we just had, and to just write down this inner product thingies. Very good. And so here is definition. So a degree D pseudo distribution over plus minus 1 to the n is simply a function mu, not necessarily non-negative, such that the formal expectation operator defined above satisfies the following properties. It satisfies one, that the pseudo expectation of 1 is 1. So the constant function, 1 goes to 1. This is just, equivalent to saying that the sum of the entries of mu equals 1, as we defined above. And 2, that for all functions f of degree at most d over 2 as polynomials over the hypercube, E twiddle mu f square is non-negative. Okay, so this is something, something non-trivial that I'm imposing on it. And I told you, at first that we're going to try to reason what properties of distributions does a pseudo distribution inherit. And this is one example of property, and I'm going to show you why it's actually natural in a bit. But what are we saying? If if f happens to be a non-negative function over the hypercube, then for every expectation, with respect to every distribution, would be non-negative, right? Now, this number 2 here is kind of, a restricted version of this fact that expectations of non-negative functions are non-negative. Okay. So what are the 2 ways I'm restricting it? First, I'm only considering f's which are low degree. Okay. So f has degree at most d over 2 here. Okay. And that goes into this qualification over here that I'm looking at degree d pseudo expectations. So a degree d pseudo expectation gives me guarantees only for polynomials of degree at most d over 2. And the other thing is that it actually doesn't even tell me that, the expectations of all non-negative degree d polynomials will be non-negative. Okay. Instead, it just tells me that expectations of all non-negative square polynomials, so which are like in some sense trivially non-negative, is going to be non-negative. Okay. So, the definition above is linear, right? Like this is a linear operator. Expectation of f plus g equals expectation of f plus expectation of g. So in particular, 2 implies that expectations of a sum of squares of polynomials is also going to be non-negative. Okay. So I guess I want to pause for 30 seconds and, just maybe take any questions if there are any, to impress upon you, the importance of this definition. So I guess maybe one thing I want you to clearly note, one thing I just like describe, which is that the property 2 here should be seen as some restrictions of properties that all expectations naturally satisfy. Good.
I had maybe a silly question about the preceding section.
Yes, absolutely.
So if f is a non-positive polynomial, why is the separation like not always trivial, and that you can always just put all of the mass on like the one thing that it's non-positive on, and all of the stuff inside of the cone is like by definition positive on that thing?
Excellent question. So so remember when we said that f doesn't have a degree d certificate of non-negativity, 2 things can happen, or one of the 2 possible situations could be true. One is that there is some actual honest to goodness x where f is negative. In that case, you're absolutely right. Just take the actual distribution that places all the mass at the x that f is negative at and 0 elsewhere. That's a separating hyperplane, absolutely. But remember, there is a second way that f may not have a degree d SOS certificate of non-negativity. It is a case where f is actually truly non-negative everywhere. Just that, it doesn't have a certificate of non-negativity. It is in that case that this, duality thing that we are doing is going to be non-trivial. We are showing that, in that case, there is some analog of distribution, analog of your idea that holds, which allows you to, in some sense, do similar to what you were proposing, to find a distribution, where f was negative. Instead, we're going to find a pseudo distribution where f is negative. So in particular, actually, Ellis brings up a very good point, and let me, repeat it in the following rephrasing. Even if f is non-negative, but f doesn't have a degree d SOS certificate of non-negativity, then we are going to prove that there is a pseudo distribution under which the expectation of f is going to be negative. This would never ever have happened if, it was an actual distribution. Okay. So in that way, in some sense, pseudo distributions are going to be somewhat more general than, distributions. They will exist even when, distribution satisfying the relevant properties does not exist. Good. Very good. So, oh no. Here is a simple fact. Yes. Every degree bigger than or equal to 2n pseudo distribution is an actual probability distribution. Okay. Actually, let me just like sketch a proof instead of proving it. um, Getting a bit greedy here. So why is it going to be true? Well, here's what I'm going to do. If so, take the function f, which is and let's call it maybe fy. Take the function fy on -1 1 to the n, such that fy of y is 1 and fy of x is 0 for all x not equal to y. So it's in some sense the indicator function of one single point. Okay. Then we know that every function of the hypercube is a polynomial of degree at most n. So in particular, fy is a polynomial of degree at most n, right? And because so if I take like if I take degree 2n pseudo distribution, then the squares of all degree n polynomials get non-negative values. Fy must get non-negative values, right? Because fy was a polynomial of degree at most n. And so what you can now prove is that if you literally take the distribution where the probability of y is simply this quantity, okay? So probability of y is simply the pseudo expectation of this fy square. Then this distribution agrees, in its expectations on all polynomials with the pseudo distribution. So we can prove, in fact, that mu of y equals this. Claim equals mu of y. Okay, so let me just leave you at that. It's very easy to verify this, but I at least give you the construction. And so this is a proof that at least every large enough degree pseudo distribution does actually pretend like an actual distribution. Okay, and this is basically the analog of the fact that every polynomial which is non-negative over the hypercube has a degree 2n certificate of non-negativity. This is basically exact analog. And again, I'm anticipating this duality theorem a whole lot, which I'm going to prove to you in a second. Good, very good. Okay, I guess I need to get another somewhat boring thing squared away. So so far, we've been dealing with the pseudo distributions. But one thing, what you might good. So trivially speaking, if I wanted to specify a pseudo distribution mu, then I have to give you its values on all possible 2 to the n points, because a priori it could be an arbitrary function over the hypercube. So in particular, the representations of the pseudo distributions could be very large. Okay, what I want to prove to you that in fact you can always assume that a pseudo distribution is a polynomial of degree at most so let me maybe write it down. Lemma for all degree d pseudo distributions mu, there exists a degree d multilinear polynomial. Let's call it mu prime, such that e twiddle of mu for all p equals e twiddle of mu prime for p for all p of degree at most d. So basically, without loss of generality, I can always take mu prime to be a degree d polynomial. That's what the content of this theorem is. So at least I can specify a pseudo distribution by giving you n to the d numbers. Again, we haven't discussed the issues of bit complexity here, but at least there is hope of some small representation for this object. Okay, so this theorem is a very simple proof, and again, like all the proofs in today's lecture, this is going to be basically linear algebra. So remember that mu x px is just the inner product of these 2 to the n vector representations of these two functions. And now I think you to do some basic Fourier analysis. So you can write any mu x as in this coefficient representation that we did before, and we can write px, and I guess because p is a degree d polynomial, the sets that will appear are at most of degree d, size d. And the only observation is that if I take the inner product of this, then, you know, basically the terms which are of degree higher than d in mu will not contribute anything. They will zero out. That's the only observation. And so, you know, what I can do is write mu as mu prime plus mu double prime, where this is the degree less than equal to d part of mu. Like just collect coefficients that correspond to degree at most d monomials. And mu double prime is basically the high degree part. And then, you know, by the following property. So let me maybe make a claim and leave it to verify. For all s not equal to t, sum over x of xs xt is 0. So, you know, these monomials in this plus minus 1 representation are actually orthogonal when seen as 2 to the n dimensional vectors. Okay, so this is very simple to prove. I'll leave you to verify this. So if you just use this, then you observe that mu inner product p actually equals mu prime inner product p, because p has no terms of degree higher than d. Okay, and so, you know, mu prime basically is our multilinear polynomial that functions, you know, as the pseudo distribution. So our multilinear polynomial. Good. Yeah, sorry I'm sketchy about this, but this is supposed to be simple. I want to go to some of the more exciting parts. But I guess we at least, you know, learned that I can specify a pseudo distribution to you without loss of generality by giving you just n to the d numbers. Very good. Before moving forward, I want to set a simple notation, which is that, you know, instead of just allowing myself to take expectations of scalar valued functions, I can, you know, allow myself to take expectations of vector valued functions by just, you know, taking expectations coordinate wise. So, you know, in particular, I can define the following notation. So this is, you know, a vector valued function. It has like n plus 1 to the d coordinates, and I'm taking expectations coordinate wise. So, you know, this is the vector that populates, you know, the expectations of all degree up to d monomials in X. Okay. Now, when you compute this, these numbers, degree at most d monomial expectations, then in the context of probability distributions, they tend to have a name. These are called as what are called as moments of a distribution, if you heard about that. If not, doesn't matter. And, you know, in the spirit of how we are doing the notation here, it's natural to call this the vector of pseudo moments. Pseudo, you know, tags along wherever there's a twiddle and where there is a pseudo distribution. So in some sense, you know, we are just lifting all the basic ideas from, you know, probability distributions, notation, etc., and, you know, just like mechanically converting them into their analogs for pseudo distributions right now. Good. So here is a proposition which has a simple proof. Mu is a degree d pseudo distribution if and only if condition number 1, expectation of 1 is 1, and 2, if I look at the expectation of this matrix valued function, it's non-negative. So again, you know, remember when we defined sum of squares proofs first, then the next thing we did was to somehow, you know, formulate a correspondence with positive semi-definite matrices. So we're kind of doing the same thing for pseudo distributions now. Okay. And so this proposition tells you some kind of correspondence between, you know, positive semi-definite matrices and pseudo distributions. In particular, it tells you that mu is a degree d pseudo distribution if and only if it satisfies the following two conditions. One is just a simple condition that we define, which is a scaling condition, that sum of the entries of mu equals 1, or expectation of the constant function 1 equals 1. And 2, and this is non-trivial one, which is that if I take the so-called, you know, in the context of distributions, this guy is called as the degree D moment matrix. And so what this fact is saying is that if you take the degree D pseudo moment matrix, then it is positive semi-definite. Okay. Hopefully there should be no difficulty in parsing this notation, but basically if you look at the entries of this matrix, just to help you parse it a little bit, it's going to be indexed. Its rows and columns are indexed by d/2 tuples of integers from 1 through n. And if you take any s comma tth entry, then the entry of this matrix is going to be the pseudo expectation of the monomial x sub s multiplied by the monomial x sub t. So the s comma tth entry equals pseudo expectation of xs xt. Remember, we already discussed that xs times xt over the hypercube actually equals xs delta t, where delta means the symmetric difference. And so, this is a very explicit matrix where the numbers happen to be, this symmetric difference moments or whatever. And what this proposition is saying is that if you are a degree D pseudo distribution, you're a degree D pseudo distribution if and only if, you satisfy the scaling condition and, your pseudo moment matrix is non-negative. Okay. So let's see a quick proof of this. So in some sense, both the directions, the first fact is obviously trivial, so let's not focus on that. The second fact, there is only one observation, which is the following. And in some sense, it's helpful for both the directions of this, proposition. So if I have any, so let f be, any degree D polynomial, degree D/2 polynomial. And let's call this maybe matrix M sub D/2, M for moment. Then the pseudo expectation of f square equals the quadratic form. Let me call it hat here. I'll explain to you why I'm doing that. Of this M D/2 matrix on f hat. So for polynomial f hat is just its vector of coefficients. So remember that f is a degree D/2 polynomial. So f hat is just, a vector of coefficients of dimensions n plus 1 to the D/2. Okay. And so the claim I'm making is that the pseudo expectation of the square of f is actually equal to the quadratic form on the coefficient vector of f of the moment matrix of the pseudo distribution, the M D/2. Again, all of the proof of this claim is unpacking the definition. Nothing non-trivial is happening, but let's do it slowly because this is kind of an important definition. So why is this going to be true? So let's look at the left-hand side just to give an idea of why this inequality has to hold. So pseudo expectation of f square equals, so let's write it down in the the coefficient vector representation. So this equals sum over s f hat s xs square. So far so good. This equals, I'm just gonna mechanically expand the square, so I can have pairs of s and t now. Sorry. F hat s f hat t xs xt. And now remember, f hat s and f hat t are constants, right? This, by linearity, I can push this pseudo expectation operator all the way inside to apply to the monomial. So let me just push this a little bit up, and I get sum over s t f hat s f hat t okay. And lo and behold, we are there. If you remember, that's how the quadratic form, that's basically the expansion of the quadratic form of the matrix whose rows and columns are indexed by s and t, and the entries are given by the pseudo expectations of the monomial given by the product of xs and xt. Okay, Again, let me pause for 30 seconds and take questions if there are any. But this is, it's a syntactic proof, but I want to get used to the notation here. Good. So there are no questions. I assume everything is clear so far. Very good. So now I want to claim that with this claim, the proof is actually done. Why is that? Well, we know that the definition of pseudo expectation demands that for every f of degree at most d over 2, the pseudo expectation of the square of f must be non-negative. Okay. By the claim we just proved, it means that the corresponding quadratic forms must be non-negative. And if you recall your homework 0 problem, a matrix is PSD, positive semi-definite, if and only if all of its quadratic forms are non-negative. Okay, so by just this claim, we have actually made a correspondence between pseudo expectations of squares being non-negative to the moment matrix M sub D over 2 being positive semi-definite. And all we used was, this characterization of PSD matrices, that a matrix is positive semi-definite if and only if all of its quadratic forms are non-negative. Any questions? Stop me. Good. I hope you're all quiet, not asking questions because everything is clear, not because it's 2.5 hours and you're dead tired and you need a snack. Yeah, unfortunately, I can't arrange snacks through Zoom. Okay, good. So, with this basic, definitions and correspondence, we can now actually, prove the main theorem or, main duality thing that we were after so far. Let's draw a line, call it a new section, and prove the following theorem. For every f and every integer d, there exists a degree d SOS certificate of non-negativity of f if and only if for all degree d pseudo distributions mu over -1, 1 to the n, the pseudo expectation of f is bigger than or equal to 0. So again, we'll take some time to parse this thingy, and let's first, try to justify why is this a duality claim. So let's, take the converse of this theorem. Take the contrapositive of this theorem. So suppose, f does not have a degree d certificate of non-negativity. Okay. This theorem says that, the only if part of this theorem says that it must now be true that there is some distribution, there is some pseudo distribution mu such that the pseudo expectation of f must be strictly negative. Okay. So what in some sense, the non-trivial and interesting part of this theorem is that if f does not admit a degree d SOS certificate, then there must be a pseudo distribution under which its expectation must become strictly negative. Okay. Good. All good. Very good. So, and again, I want to, so there's a lot of notation and jargon that I'm introducing. Everything that I'm actually doing is simple, but there's a lot of information. So, I want to repeat and have redundancy so that, if there are any issues, I catch them somehow. So let me repeat the following claim. Remember that even if f is non-negative over the hypercube, it may not have a degree d SOS certificate of non-negativity when d is much smaller than 2n, in which case this theorem says that there is a pseudo distribution under which the pseudo expectation of f is strictly negative. F was strictly positive everywhere, but its pseudo expectation is still somehow negative. Okay, that's what this theorem is saying. Good. So let's prove it. The if part of, so let's, first prove the easy part. So, and it's simple, so I'm going to be quick with it. So if F has a degree D certificate, then I want to prove that for every pseudo distribution of degree at least D, the pseudo expectation of F must be non-negative. Okay. Why is this going to be true? Well, F has a degree D certificate, so we better start by using it. So F can be represented like this. Good. And now I'm just going to apply linearity and take expectations on both sides. So take any pseudo distribution in the world, then pseudo expectation of F equals sum over I by linearity. It equals pseudo expectation of GI square summed. And now remember, GI have to be of degree at most D over 2. The second condition in the definition of pseudo expectation of degree D demands that on squares of all degree at most D over 2 polynomials, your pseudo expectation must be non-negative. So this right-hand side is a sum of non-negative quantities. So is non-negative. Okay, this was simple, but hopefully clear. Good. So now let's do the only if part. That's a non-trivial part where we'll use the separating hyperplane theorem. This is basically formalization of the discussion we were having earlier. So now suppose F is not contained in the degree D SOS cone. Okay. As we discussed, there is a half space, and let's say mu is the normal vector. Yeah, good. And now we have notation for talking about the inner product. So in particular, we can conclude that with respect to, and so mu, the normal vector must be non-zero. This just comes from the separating hyperplane theorem that mu must be non-zero. So we can immediately conclude that E mu of F is less than 0, and E mu of G square is bigger than or equal to 0 for all G of degree at most D over 2. Why is this part true? Well, because if G is of degree at most D over 2, then G square certainly has a degree D SOS certificate. So G must belong to this cone. So hopefully you agree. This is just a restatement of what we discussed earlier. We have these two facts that mu is a separating hyperplane for the SOS D cone, and this point F, which is not contained in it. Okay. But as Alex pointed out, what have we not proven? We haven't proven that tilde E mu is actually 1. That's what we are lacking right now. Okay. So what remains? It remains to be shown that tilde E mu of 1, so I'm going to claim that anything bigger than 0 is enough, because if it is bigger than 0, I can just scale it and make it 1. And because these two claims above are scale invariant, it will not really affect them. So are you all convinced? And ask me questions right now if you're not, that all that remains to be shown is that the pseudo expectation of the constant 1 function, which is same as saying the sum of mu x's over all x's, is strictly bigger than 0. Okay, very good. So I am going to use a claim here, which I'll prove right after I complete the proof here. Here's the claim I'm going to prove. For all functions f, there exists some quantity, let's call it L for large, such that L plus f has, suppose f is a degree D polynomial. There exists a L large enough such that L plus f has a degree D SOS certificate. Okay. So let me maybe parse this claim out for you. I'm going to prove this to you in a second, but let me parse it out for you. So what his claim is saying is that, no matter what f is, so f could be negative, by the way, right? F need not be non-negative here. F could be an arbitrary polynomial. All we're saying is that, there is some large number L that could depend on the coefficients of f in however, in whatever manner. So that L plus f, like shifting f by some large number L, adding a large positive quantity to it, will make it, have a degree D SOS certificate of non-negativity. Okay. So to get intuition for why this might be true, let's consider D equals 2n. Okay, let's consider the case when degree D is 2n. So you're looking for degree 2n certificate of non-negativity. In order to, refresh what we've just learned about an hour ago, having a degree 2n certificate of non-negativity is equivalent to L plus f being truly non-negative over the hypercube. So what this lemma in that particular case is saying is that for every polynomial f, there is some value such that some large positive value that you can add to it to make it always non-negative, which is obviously true, right? If f is a polynomial, take its minimum value. Let's say it's minus L. Add L to the polynomial. Now it's going to become always non-negative. Now this is for the special case of degree 2n. What this claim is saying is that an analog of it holds also for low degree SOS proof. So even when f is any degree D polynomial, then there is some number large enough that you can shift it by to make it have not just non-negativity property, but also the property that it has a degree D SOS certificate of non-negativity. Okay, good. So hopefully this is digestible, even if not proven yet. So let's use this fact to actually complete the proof. So let's look at, so the only non-trivial information I have is that e twiddle mu of f is strictly less than 0, correct? That's what mu satisfied. That's what we got from the separating hyperplane theorem, right? So let's shift it. Now, we said that L plus f has a degree D SOS certificate. So it must hold that e twiddle of L plus f is bigger than equal to 0, right? Because L plus f has a degree D certificate, meaning L plus f must be a sum of squares of degree at most D over 2 polynomials. Because because e twiddle mu of any degree D over 2 polynomial, the square of any degree D over 2 polynomial is non-negative, it must hold that e twiddle mu of L plus f is non-negative. So far so good. So I claim that we are done now, because we're just going to do some shifting business now. So we have, minus e twiddle mu of f. And remember, e twiddle mu of f was strictly negative, which means minus e twiddle mu is strictly positive. And by linearity, the left-hand side equals L times e twiddle mu of 1, right? So we actually derived that L times e twiddle mu of 1 is bigger than or equal to minus e twiddle mu of f, which is strictly positive. So, this allows us to conclude that e twiddle of 1 is and that's it, we're done. So let me draw a little square. Modulo the claim, of course, which I'll prove to you now. But any issues with this proof so far?
Thanks.
Good. So let's, in the remaining time, I want to, yes.
Sorry, can you repeat why if f plus L has a degree 2n certificate, then it has a degree D certificate?
No, I didn't claim that. Sorry, I guess my informal discussion was a little bit ununderstandable. So what I was telling you earlier was some intuition for why you should believe this claim even without a proof, even though I am going to prove it now. So I was telling you, look at the special case of D equals 2n.
Okay.
In that case, I'm saying that the claim is simply saying that, for every function, however negative, there is a number you can shift it by to make it always non-negative.
Yes.
Right. And so, in some sense, I was just trying to point out that it's an analog of that statement. So you should believe it to be true.
Okay.
Good. So, but, let's not believe it anymore because we can prove it. Okay. And the observation is the following. So, what we will prove is, so, let's say F is, S, remember S is at most D, F hat S, XS. So what we're going to observe is that 1 minus XS has a SOS proof of non-negativity. So 1 minus XS has a degree D certificate. Okay, this is what we will prove. This is claim within a claim. But at least you see that if this is true, then we are done. Why are we done? Well, because if 1 minus 1 minus X and also 1 plus XS. So I guess the claim I'm making is that, if you shift any monomial by 1, then it always has, a degree D certificate. And I'm going to claim that we are done using this. So what am I going to do? I'm just, going to take F and write it as F hat S 1 minus XS. Okay, wait a second. Sorry, let me get my notation right. So let me write it like this, okay? Sine of F hat S, X sub S. Okay, and then, I'm just going to observe that if I do 1 minus this guy, then, by this claim, 1 minus this sine of F hat S times XS has a SOS certificate, right? So this equality doesn't hold anymore. So what does this mean? It means that sum S F hat S minus sum S. And now, I basically recover the polynomial. So, but let me write it like this still. So I'm claiming that has a degree D certificate. So I want to claim that by this claim that I have not proven, but I hopefully have reduced my task to, if I use this claim that shifting by 1, if you shift any monomial by 1, then it has a degree D certificate. I can use that to prove that this particular polynomial, where I've taken the absolute values of the coefficient of F, absorbed the sign in front of the monomial, right? And shifted it by 1. Okay, or, oh, sorry, I should have plus maybe. Okay. And then I just observed that this equals the sum of the absolute values of the coefficients of F plus the polynomial, which is actually equal to F itself. And so, what this proves, modulo this claim about monomials, that if I somehow, prove this claim for monomials, then I have actually proven it for all polynomials, where my large number is simply this. Is it clear? Again, hope the quiet is because of tiredness and not because I'm not making any sense. Snacks. All of us got to have some snacks. All right, so let's do the claims. Yeah.
Oh, for the previous claim, was it for all L large enough, or
No,
was
no.
it there exists an L? There exists one.
There exists an L large enough. Yeah.
Like a single one potentially.
So ponder over this, and we can come back to this in 5 minutes. But I claim that if L works, then anything bigger than L also works.
Okay.
Okay. And the only observation is that a positive real number is also a square. So, you can take L and take whatever you're adding to it and consider that as a term in your SOS representation. If that didn't make sense, don't worry about it. Just think about why, if L works, then anything larger than L should also work. Okay, let's prove this claim, okay? And it's actually going to be very simple. So, oh, sorry. I should have said that this is a claim that's going to be proven only for even D. But that doesn't change much. So now let's say that, S is, so that let's divide into two cases. S is of, exactly a degree, S is of exactly size D and, otherwise. So let's, deal with this case because in some sense it's the only non-trivial one. So the observation is that I can take S, so S is of size D and we are assuming that D is even here, which means that S can be written, as arbitrary take an arbitrary partition of S into, two sets of size D over 2. Okay. Then, we know that X sub S equals XT1 times XT2. Good. And now, all we are going to observe is that XT1 minus XT2 square equals XT1 square plus XT2 square minus 2 times XT1 XT2. Remember, we are over the hypercube. So XT1 square and XT2 square actually equal 1. So this actually equals 2 minus XT1 XT2. And we have a square here. So rearranging gives 2 XT1 XT2 equals 2 minus XT1 minus XT2 square. Wait, did I do it right? Wait, sorry. That's not what I want to do. That's a useless step. I guess all I want to do is like divide by 2 throughout. So I guess what I have proven is that 1 minus XT1 XT2 equals half of XT1 minus XT2 square. So, this proves, and remember XT1 XT2 is XS. So, this is equivalent to 1 minus XS equaling half of this guy, which is a square. Okay. So I've given you proof of 1 minus XS being a square, and XT1 and XT2, remember, were of degree D over 2. So this is a square of a degree D over 2 polynomial. So this is the degree D certificate of non-negativity for 1 minus XS. Okay. The other claim is also very simple. I just work with plus instead. And, by the same argument, I arrive at this expression, which when I rescale gives me 1 plus XS equals half XT1 plus XT2 square. And that's a degree D over, that's a degree D certificate of non-negativity of 1 plus XS. Now, you can do this. So, in some sense, this was a non-trivial case because S was of size exactly D. If, you are of size D minus 1 or smaller, then, you can take any. So you can see that this argument works whenever I have a partition of S into 2 sets, each of which have size at most D over 2. And then I can run this same argument again. And the point is that, in some sense, the exact case was in some sense a non-trivial one. Everything else is somehow the same. Okay. So that's the proof of claim. Going back, that was a claim, proof of this claim here. Let me, make some pointers. And we use that to prove the claim about all polynomials. Going back, we used that to prove this claim, which, went inside the proof of duality. So by unfolding everything, we've actually, proven this duality theorem. Okay. Good. So, I don't want to like take your, try your patience too much because it's already like 2 hours and 50 minutes, but, just 2 minutes about what's coming up ahead. So, today we kind of saw very basic concepts, sum of squares proofs. So, when they exist, what happens when they don't exist. We proved a basic duality theorem. One thing that we haven't absolutely discussed so far is algorithms. In particular, we haven't defined this mysterious sum of squares algorithm for testing feasibility, etc. Okay. So in the next class, what we'll do, the first thing we'll do is, discuss algorithmic ideas, the issues that, arise when you deal with them. And in particular, how semi-definite programming can be used to find degree D certificates of non-negativity and, degree D pseudo expectations when they don't exist. And then, we will use them to see our first spectacular application for solving the max cut problem. Okay, that's our plan next time. And officially the class is over now. But I'm going to be around for a few minutes to see if there are any questions and I can answer them.
So I was wondering if there are any alternatives to sum of squares to proving the non-negativity of a polynomial. Like because clearly squares are non-negative, but then yeah, I was wondering if you can use other building blocks like exponentials, for example, which are also non-negative.
So it's a very good question. So the answer is obviously yes, right? As you've already suggested, there are other building blocks, other like basic primitive functions which are always non-negative, as you said, like exponentials. And in principle, you could try to define like some hierarchy of certificates which uses those kind of functions. And not only is this like a hypothetical, it has been done. And so, if you go back and, Google search for relative entropy hierarchy, you will see, some certificates based on, positivity of entropy. And there are also, I think, I'm not totally sure if the exponential thing appears somewhere, but probably does. The issue obviously is, which kind of certificates, okay, they're like, once you think about the certificates, you end up with like two natural questions. Can you somehow replicate this kind of theory, that we know for sum of square certificates for this other class of certificates, right? So in particular, is there some algorithmic primitive that will be able to find those certificates? We haven't done that right now, by the way, for SOS certificates. We're going to see it next time. But in some sense, that's what makes it powerful, right? Like the fact that whenever these certificates exist, we can somehow calculate them. We can compute them. So you have to think about those. And the other thingy, which is perhaps even more important, is that what can you do with them? Which problems can you solve with them? Can you solve interesting problems with them? And there are like several proposals right now, and all of them are tied down to very interesting questions in geometry and optimization. But I guess so far we haven't found killer applications for these other kinds of certificates and the associated hierarchies of optimization problems. We have been able to find what I would at least call killer applications for SOS and in particular semi-definite programming. We haven't succeeded in doing that for this other variant of those notions. So yes, the answer to your question is that yes, they do exist, but we haven't succeeded in finding applications which are striking yet.
So ignoring computational issues, you can show that a non-negative polynomial can be written as a sum of squares of rational functions. This is a
good. So I didn't discuss too much of the history because, well, it was a conscious choice. You can do too much of history and then too little of math. But basically, what Anish is asking is, is like, in some sense, the way this SOS business arose was, as in some sense, all good things do. I think the story, okay, I hope that I did this part of the video out so I can talk about this. So I think Lagrange actually, proved his, for this famous like four square theorem for integers, which basically says that, every positive integer can be written as like sum of four squares or something. And then, Lagrange was concerned whether it's true for polynomials, because usually, in some sense, whenever something holds true for ring of integers, you expect it to hold true for ring of polynomials. And, Hilbert basically found a counterexample. Actually, he didn't find a counterexample. He proved that there is a, so, Hilbert, I think this is, if I remember correctly, maybe 18 something. So let's say, late 1880s or something. So Hilbert basically proved that there are non-negative polynomials over the reals. So, this is unbounded domain, which are not SOS. So on your homework, you're going to prove that every univariate polynomial that's non-negative is SOS. But it turns out that if you go to multivariate polynomials, this is no longer true. And Hilbert observed this in 1889. He gave like a non-constructive proof of this, unfortunately. And for whatever reason, even though they're very simple examples that we know now, it took until about 1960s to find like an explicit counterexample. And that's what the Motzkin's polynomial that Tim was referring to earlier. So, but, Hilbert wasn't going to stop at that. So, in his 1900 famous address where he, gave these essentially, how should I put it, a manifesto for mathematicians to attack, which we in some sense are still attacking. One of the questions he asked, which is his famous Hilbert's 17th problem, So, Hilbert, before, all computation, etc. existed, he was still thinking about certificates. He didn't know NP, but he was still, asking for like, how can you give certificates of non-negativity of polynomials? So he said, well, the good thing that sum of squares did was like, it gave like a verifiable certificate for non-negativity of polynomials. It doesn't exist. So I can ask what other kind of certificate could still exist. And so he conjectured that every non-negative polynomial can be written as sum of squares of rational functions, meaning, ratios of, polynomials. And so this was his 17th problem. It was actually one of the first few to be resolved. And so Artin in 1927 proved Hilbert's conjecture, or solved Hilbert's problem. And actually, in some sense, Artin's theorem is the very basic example of what is called as a positive Stellen-Sart's theorem. I never get the pronunciation right. Thing that I referred to earlier, in some sense, these are representation theorems for non-negative polynomials. If a polynomial is non-negative over a domain, can I say something about, how it can be represented in some simple, nice way? So sum of squares is like one such representation. And, these theorems in general, positive Stellen-Sart's theorems in general, give you ways of representing such non-negative polynomials. So Artin basically solved the question over, unbounded domains. And then over the years, these have been refined to work over more and more general domains. And so in some sense, when we go to the general SOS machinery, when we do like polynomials over general, domains, we're going to, use the generalizations of Artin's theorem, in particular to Quirine, about 64, independently due to Stengel, but he didn't know of Quivine's result in 74. And actually, there are improvements to these theorems due to Putinar and Smudgen. So, these are all theorems that under various, and in some sense, their attempt is to, make as little assumption on the domain as possible and prove representation results, for positive polynomials. And these are, in some sense, these are results that guarantee that SOS certificates exist on, SOS certificates of non-negativity exist on, other domains. So I don't know exactly the question you asked, Anish. I took it as a, cue to say my story.
Oh, I was just saying as a follow-up to the previous question of representation. So if you don't care about computational aspects, you can represent negative polynomial as a rational function.
Or unbounded domains. Yes.
Yeah.
So, we are mostly going to be concerned about, bounded, in fact, explicitly bounded domains. And again, I have not defined that, but, basically these are domains defined by, polynomial inequalities, where the inequality sum xi square equals to some less than equal to some number is included explicitly. So that's what I call explicitly bounded. All of our applications are always going to be on explicitly bounded domains. And on such domains, in some sense, we always have a certain completeness result. We don't have to rely on, at least the kind of domains we look at, we'll rely on very simple versions of positive Stellen-Sart's. But you're right, even on unbounded domains, there is Artin's theorem, except that, the certificates have to look like squares of rational functions, not of polynomials. You can also use this time, by the way, because I'm going to hang around for like maybe 5 to 10 minutes more to, give suggestions or, point out issues that may have, you may have faced during this lecture. For example, technical questions like audio quality or video quality and things like that. So if you have any other, comments, suggestions, complaints, you can tell me right now. I can try to fix it for the next few lectures.
So Pravesh, can we review the proof where you showed that every pseudo distribution of degree greater than 2n is actually a probability distribution?
Yes. Yeah, let's do that. Where was that? Let's see. Oh no. There it is. So let's see. So, what this proof is trying to do is like literally, sorry about the light. somehow, I was relying on Pittsburgh being cloudy all the time, but apparently it's not always cloudy. Okay, so, yeah, so, what I want to prove this fact is by, just explicitly giving you a construction of a distribution, okay, that this pseudo distribution corresponds to. So what does that mean? I want to give you a probability distribution such that if you compute the expectation of any polynomial with respect to it, then it matches the pseudo expectation of that polynomial. Okay? And so here's my construction. I'm saying for every point y in the hypercube, there is a function that somehow, gives that point the value 1 and 0 otherwise, right? So that's what I've written down here. There is a fy such that, fy of y is 1, and at every other x, fy is actually 0, right? Yeah. Good. And so now, in some sense, if I was an actual distribution, then notice that expectation of fy would simply be the probability of y, right? Because this is the indicator that the random variable outputs the value y, right? And so in some sense, taking expectation just literally returns to me the probability of that. So for actual distributions, if I did the same operation, I would end up with the probability. That's the intuition anyway, right? Make sense? And and the other thing I should have mentioned explicitly was that fy square is fy, right? Because it's a 0, 1 valued function.
Yeah, of course.
Okay. And so now all we are using is that because fy is fy square, and because fy is of degree at most n, because that's literally true for every function on the hypercube, and mu is a degree 2n pseudo distribution, the pseudo expectation of fy square must be non-negative.
Yeah.
Okay, so it's legit to call it a probability, right?
Yeah.
And so now, what do you have to verify? Well, first you have to verify that this is a well-defined notion of probability. And so, for that you observe that, okay, let me write in yellow and I can erase it later. So the only thing to observe is that sum over y fyx square actually equals the constant function 1. Which is again not surprising, like literally fy picks out one single y, so they add up to 1. And so by linearity, expectation of this guy must equal 1. Because mu is a pseudo distribution, so expectation of 1 must be 1, right? And so at least I've convinced you that what I defined you is a legit probability distribution. It's always non-negative and it adds up to 1 on the hypercube.
Yes.
Right? And so now the only thing to check is why are the expectations going to agree? Right? And again, this is another application of the fact that all functions on the hypercube are polynomials of degree at most n. So just take any function. Let's say take gx and write it as g of x. Let's see, fx. Okay, did I do that correctly? G of x times fx, and now okay, good. No, I think I did it right. So I guess. Sorry, one second. Okay, I'm just trying to get my notation right. Also need another snack. So now, think of this as a function of the variable y. Okay. So I claim that if you look at this function, then this actually equals g of y. Good. Got it right.
Right.
Okay. And so now, the proof is done because take pseudo expectations on this side. Yeah. Remember that gx here is a constant. Right? Like the pseudo expectation is now, in the variable y. Or actually, I'm confusing you. So let me write it like this. Right? One last time. So I guess I'm going to say that gx equals gy fy of x sum over y. Okay, now it's correct. Now take pseudo expectations on both sides. Remember, gy is a constant because our pseudo expectation is in variable x. And fy is fy square. We know that, there the pseudo expectations and expectations match. And so, we have proven by linearity that the, that the expectation with respect to this distribution that we just defined equals the pseudo expectation under mu.
Yeah.
Does it make sense? It's a whole lot
Yes.
of notation, and I was trying to still